begin with something which is essential for people to learn before diving into the depth of the proofs. That is the declared convolution, and declared function. Because this, product of declared function is intertwined with the declared convolution. So first, let's introduce what is convolution of functions. But even before that, let's define what are arithmetic functions. What are the rules? Just some function from the set of natural numbers to the set of complex numbers. So just some sequence. Now, please pay attention because soon we are going to solve exercises, easy exercises. These are just fast on this. So, then additive functions are those of the form f of m in m. Maybe I just write this instead of just brackets. It's additive functions. And then there are multiplicative functions. Now these are called additive or multiplicative functions, and if you do not require this condition of this g of m and n to be equal to 1, then you call them if these two equations, or for all m and n, without this condition, we have, not necessarily having this condition. That is, for these ones we have this, and also for the ones which do not satisfy this, we still have f of mn plus f of n plus n plus f of n. We call it completely additive. These are called f is completely additive. And if for all in n we have f of mn as f of m times f of n, we say that f is completely multiplicative. So your first exercise, give me examples of such functions. How much is it? 80%. Otherwise, is there any charging port? And is it being used for this one? Huh? Yeah. Oh, we computed it. Please, left. Or otherwise, if it runs straight out, you can ask the participants to join in the stream. additive and complementary multiplicative would be easier. Yes, sir.
If x equals to x squared, can be completely multiplicative.
If x equal to x squared is an example of a complementary multiplicative. Meaning, yeah. Yes, of course, an example is if x squared is squared or any order. Okay, so this is completely multiplicative. How the other three cases?
So e to the power x completely additive.
Perfect. Completely additive. Wait a minute. E power x. I mean, e power n is not e power n plus e power n. Log. Right. Yeah. Log x is completely additive. And the other examples like completely additive and multiplicative.
Quotient function.
Yes.
Quotient function.
Euler quotient function. Yes. Which one?
Additive but not complicated. Sorry, multiplicative but not complicated.
Multiplicative and complementary. Right. So Euler quotient function is multiplicative. But not completely multiplicative as we just mentioned, because it will be right.
4, 6, 5, 4, 6.
And
4 into 6.
4 into 6, okay. So phi of 4 is 2, and phi of 6 is 2 also, right? And phi of 24 is what? It is that you are counting the numbers which are less than 24. And yes.
4. 4
Yes.
into 2, 8.
So this is your example. That's, but you could have taken phi of 2, phi of 4. So you didn't have to compute what is exactly quotient function for 24, but you would have just counted how many things are less than the number that you are considering, and you just go right to this. Okay. And that leaves you with only one example of a completely additive function. I think that is not too obvious, but if you could give me an example of that.
Additive but complicated.
No, yeah, right.
Log of 5.
Log of? Okay. Let's see. Sorry. Write this one. Log of. I know music, right? So let's say, at first it should be additive, right? And since phi of m is equal to phi of m and phi of n, you get that log of phi m is equal to log of phi m plus log of phi m, right? And then it is not completely additive because phi m is not completely multiplicative, right? So we just saw the example of all these kind of functions, and now I would like to introduce two more functions. One is this one, Mobius function, which will be very helpful in convolutions. So can I write this button? not divisible by square root of some prime, that means it's just a product of, say, r many primes or k primes, right? So for those square free numbers, mu n is defined as minus 1 whole power k if n is a set of a product of some ei1, ei2, it's a product of k primes. So of course this and the first thing will be clubbed together because here the set of lines dividing n is just the indiscriminate. So there is 0 primes. And then you get getting just minus 1 over 0. So can you tell me which kind of function mu n is? Multiplicative, additive, completely multiplicative, which kind? It's a multiplicative function. And why not completely multiplicative?
If there is any common factor, then x is
Yes.
not square.
If you multiply, then on one side you get a square root prime, which makes the other side, I mean, that side is it. Whereas other side you have minus 1 power something and minus 1. So in it is a multiplicative function. And now we are going to define a function which is neither of any of this form, and this is what is a very important numerical function which will occur again and again. Well, of course, mu will occur, and also this one, lambda or von Neumann function. So this is defined as log p if n is a power of some prime p and 0 otherwise. So for every n which is a power of prime, this function is log p, otherwise it is 0. Okay. Any questions? So we have already seen this function just a while ago. Where?
Solution second function.
Very good. Yes. It was in second tips.
Second function.
There we define it with xix as the sum of log p such that your k is greater than x. Right. What we are doing? We are actually summing the one-man-word function over all the things which are less than x. So this is nothing but the sum of lambda n, sum of lambda n less than x. So such things, that is, where you are going from one function, summing over it over the integers which are less than or equal to x, or we will also sum over divisors. So, I mean, whenever you are given some basic function and you are summing over it to get another function, we call this one the summatory function of this one. And what we mean by summatory function, it will vary from case to case. Sometimes it will be less than or equal to, I mean, such things. Mostly it will be such things. But till the time when we are in the domain of decayed convolution, this sum, I mean, sometimes this sum will be instead not in less than or equal to x, but summing over the divisors. It will come soon. So once we define the convolution of the functions, let's define it immediately actually. see that this is shown with the number theory function or arithmetic functions. There we wrote number theory function. Here we are writing number theory function, and there we wrote arithmetic functions. They mean the same thing. So here, now we note a few things about the convolution. The first thing is that it's commutative. Of course, you can replace d by n by d. So this very easy this. Now the next thing is that is there any identity element of convolution? That is, what I want to say is that inside function some identity function. So some function with which you take the convolution of f and you get f back. What function it should be?
One where n equal to 1 and 0 otherwise.
Very good, because we just want to get f of n out, right? So here, when this is n, this will be just 1. Right? For everything else, it will be 0. So define this function, say, let's call it the unit function. Where should I define it? Here. Define that u n we defined as 1, n equals 1, 0, otherwise. Then note that f star u is just f, right? First of the definition. So this function which we defined in this one here, actually, this you can also write as un is just a box of 1 by n. You see? Because for n equal to 1, it is giving you 1. For everything else, it is just 0. So this is the identity function of liquid convolution. So I got commutativity, and associativity is actually trivial. I mean, if so this is commutativity, associativity, if star g star h. Yeah, it is actually trivial because here you are, what do you mean? You are taking, you are doing the convolution reverse. It's like e divided n f star g of. Well, there's a tutorial session. Maybe you should try this. Try to show that this is associative, and it's not a very difficult. So please take. And of course, we could write it in this manner, but you can write it also in some other manner, and then we rather easy. And next we have to break this one, right? But if you simplify the notation a bit, then this kind of outputs. So you won't have to even manipulate the brackets. how we to proceed. You just wrote it down in this manner and then wrote D like this and proceeded, or you do something else. You are Shanta. Sure. Sorry. Alright. So yeah, that actually makes life much easier to write this in as a product of more than one or two factors. So it's actually you are doing the same thing, but just in a different way. So we define that f of d times g of a by d, where d is divided in. Right? We could have written this also as summation over d times d dash equal to n f of d and g of d. Okay. So we are writing the same thing here and there, right? I mean, just the notation is different. So if we do like this here, then this one, this of n of course, instead of writing it in this manner, we can write it as product over three things. Well, at first product of two things like this d and d dash whose product is equal to n. Call this d, I mean instead of d dash, call this d double dash. And the first one, first factor here, well, you can call it d1 and d2 maybe. Okay. d1 for this one, d2 for this one. Their product is equal to n. Okay. Now you write it, this f star g of d1 as there's a product of some factor of d1 times some other factor of d1 whose product is giving you d1 and the product of them all is giving you n. So this would be just the sum over f of d of d dash and h of d double dash. So at first you club it like product of d dash and d dash and then break it. Basically you are also doing the same, but this gives off the associativity immediately. So this can be written as a star a of n. Right? It's just one line. I'll do the computation. It's a very nice. Okay. Now immediate application as an immediate application of the associativity. So wait a minute. We still got associativity and identity. We haven't even yet proved the inverse, right? I mean, what we are trying to do, we are trying to show that this function, this convolution is giving group law over some set, over some set of arithmetic functions. So we'll go into that very soon. But first, consider this one. Actually, instead of denoting it u, since it's an identity, we can denote it by I. That would be easier. It's the identity function of every convolution, right? So, because we will call something else the unit function. The unit function will take 1 at all the inputs. Define the unit function with un, which is equal to 1 for all n. And let's first compute the convolution of mu with u. So consider the sum over, well, just compute this. mu star u of n. What is that? U is identically 1 for all n. We call it the unit function. The identity function, well, for identity function, let's use the notation I because it's easier to denote. It's easier to identify if we use I because I for identity. And we just saw that if we use this function box of 1 by n, then this is actually giving this. For any function f, if you take the convolution of this with identity from left or right because it's commutative, you get f back. Now the question is that if you are considering this function instead u, and if you are taking the convolution of mu with u, what are you getting? The identity function. Okay, let's check the summation mu d and well mu d times u of n by d, which is equal to 1. So we don't even need to write d by d n. Okay, and then why is the identity function? Okay. What you require for this to be an identity function, that it is taking the value 0 for all n's larger than 1. Otherwise, at 1 it's 1, it's obvious, right? Because mu d is just mu of 1, which is equal to 1. So this claim is of course true. It's trivial. 1 if n is equal to 1. So all you require is to show that this sum mu d dividing n, this is mu 0. The question is why.
We can factorize n as a distinct time.
Yes.
Like if n equal to p1 alpha 1, like p n alpha, that will be the summation will be equal d divides p1 p2 over pn,
Right.
And we can use the binomial theorem that thing that will be equal.
Okay. Very nice idea. Actually, I can do that. So since mu is multiplicative, we can write mu d as the product of the mu distributed over the prime powers, that is dividing d. And of course, if d is divisible by some square, then it is 0. So all you have to care about the primes, which is as long as d is square free, we only have to work with that. So then mu d divides n, what will it become? Product of sum over, say, p1, p2, pk divides n, mu p1, pk, right? That is the sum is over only the co-prime divisors. Sorry, square free divisors of n. Okay, that is the prime product of the primes which are dividing us. So now this one is just the sum over p1 pk divides n minus 1 will got k. Okay, but that's not what you said, right? You said that divide this instead. Divide n.
We take d divides p1 p2
Right.
pr.
Of course, yes. So we write n as p1 power p1 power pk power ak, and then mu n is equal to mu p1 mu pk ak, right? And so you can do the same thing with d, right? So so instead of writing d case here, you want to write this sum mu b as one plus mu p1. I mean, if sorry, if n is of this form, you just want to write this sum mu b as just mu p1 plus mu p1 or a1 times 1 plus mu p2 plus mu p2 power a2 1 plus mu pk mu pk power ak. Right? That's the thing we want to do. And then you just have to look at here because the rest are all zeros. Right? That was the idea, or that was not. So what was the idea?
Like this n equal to some p1, a1, p2, a2, like pr, pr.
Yes.
Then you can do the summation equal to n divides, sorry, p divides p1, p2, pr. Because it does not depend on the square factor.
Yes.
You can just take the distinct line.
Yes.
All the distinct line.
Right.
P1, P2, pr. You can do that. G divide P1, P2, pr.
Yes.
And mu of d.
Okay.
Then we can that time we can think about how many.
All possible product of primes from all possible square free numbers which are dividing n, right? And there will be 2 power k such things, right? You can take any of the any of the primes dividing that, or you cannot choose any. So that will, if you don't choose any, that gives you 1, and for everything else you are getting those many primes. So you have 2 power k choices, and then for each of these 2 power k choices, it's just minus 1 whole power the number of primes. Right?
You can use 1 minus 1 to the power k, some just binomial is
1 minus
1 minus 1
1
to the power k.
1 minus 1 to the power k. Right? Of course. Yeah. Sure. That's a very nice idea. Also, you can so is this clear what we wrote there? It's basically the same thing, because you see all the higher powers vanish, and then you have 1 minus 1 here, 1 minus 1 here, 1 minus 1 here. So it is basically 1 minus 1 to the power k. Exactly what you said. So each of this turns out to be 0. Well, what we are saying is that mu power pk is equal to 0 for not only mu power pk, sum over this for k running from 0 to any n, any arbitrary n. Right? And then since mu is multiplicative, sum over the divisors of n would just be products of such things. And each of the factor is turning out to be 0. So when you multiply finitely many zeros, we get 0. Alright. So indeed this is giving you that mu d is equal to 0, and sum over mu d is equal to 0. That means that here we are having that the sum is equal to 0 if otherwise. Okay. So yes, as you identified, mu star u, this is indeed giving you the identity function. Alright. Now time for a very short exercise and nice exercise. Okay. Let if n be the sum of some function f over the divisors of n. prove that if f is equal to f star that is Fn is equal to summation Fn times mu Fd times mu n by d, d dividing n. And it's a very short exercise because we have everything that we require for this. Is the charge is gone, but you wrote the people to go to the stream.
Actually, we can write that capital F of n equals to summation d divides n f of d
Yes.
into u of n by d.
F as again. Capital F as
In the first line,
the first line. Yes.
there is only f of d.
Right.
That means f of d into 1, and we can write 1 as u of n by d.
One as u of n by d, right? Yes.
So it becomes f star u.
Right.
So if we take u in the other side, then it gives f star mu.
Okay. We can actually, but you can also convolute this with mu, right? I mean, you don't need to.
We
It's the same actually. On the other side means that you wanted to invert it,
Yes.
and that means just convoluting with mu, right? Because mu is the inverse of that. So indeed, that's the idea. So since f is equal to f star mu, and now that implies that f star mu is giving you f star u star mu. Okay? And you know that associative is there, that's why I have not wiped out this line. So that means you can do this fast. And if you do this fast, you get I here. So this is f star I, which is giving you f. Okay. So now another exercise. Is show that lambda n, the polynomial function, is equal to sum over mu d log of n by d, d dividing once you are done, please let me know. Yes.
You can do the same way, I think distinct factorization.
Yes. Right. So, so we are trying to show that lambda is mu star log. So then what we should show? I mean, what suffices to show?
You can do the D divides that you have to do that way.
Yes, yes. Okay.
Same way you can do that.
Actually, the same way.
Exactly. So tell me, you should take the convolution with what?
That way.
The inverse of mu, right? And what is that? U. The unit function. So this is equivalent to show that lambda star u is equal to log. That is log of n is equal to lambda star u n. Right? So that implies you have to show that log n is equal to summation lambda d dividing n. Right? Now, what does it mean? Summation lambda d dividing n. That is, you are summing over the prime divisors of n, because not prime divisors, the prime power which are dividing n. Right? So that means summation log p such that pk is dividing n. Right? So that is what summation over p. Wait, what do we do after this? For each prime Vp is equal to n, we are taking the sum over sum of log p as many times the power is dividing this. So that means if n is equal to p1 power a1 dot pr power dr, say, then log n. Well, at first, just look at this. What is log n? Log n is summation ai log pi. I running from 1 to r. Isn't this the same expression? Aren't these two? Because here you are counting the primes. You are summing over log p as many times as the power pk divided by this. Right? So you are actually counting once this for p1, p power 1, p power 2, etc. up to p power k. That is, you are counting for all these powers. So this is basically exactly the same expression, summation log p less than equal to n, that is all the primes less than equal to n, such that pk, well, the sum is running for over all the primes, that is obvious because it is just writing that pk is dividing n. The pk is the highest power. Well, not exactly the highest power. Actually, this is running from over each power of the prime p and p prime. Okay. And of course, we require that k is greater than equal to 1. Okay. Because otherwise, we will have log p contributions from the other primes and the primes which are not dividing this. Okay. So this is basically the thing that we wanted, right? So this is just sum over d dividing n lambda n. Okay. And d dividing n lambda n means that this is summation dividing n lambda star u n. So log is lambda star u, and therefore lambda is equal to mu star log. That's it. Ah, right. Thanks a lot. Yeah, here is also. Thank you. So now the next thing. Now the next exercise is even funnier, and it is you know this function, right? The Euler Cauchy function. And you know the expression of this phi is equal to product over, well, n times product over 1 minus 1 by t divided n. Now start with that description that phi of n is the number of coprime integers. Sorry. Coprime to n and less than or well, it cannot be equal to, of course, unless n is equal to 1. So less than n equal to 1 actually claims this for n equal to 1, little descriptive here. So equal to n. Okay. And suppose we don't know this. We have only this description of phi. That is, we are counting all the numbers which are less than equal to n and coprime to n. Show that. Using whatever we have done till now. It's a nice exercise. 2 minutes. Yes.
So first, I write phi in terms of the identity function, which is k equal to 1 to n, identity of I of GCD of n.
Let me write it down.
You can do that question.
We can do the prime decomposition, but first then we must prove that this is, this one. We took that as an example, but we want to prove this. Yes.
So phi n equal to summation of k equal to 1 to n. Summation k equal to 1 to n.
Okay.
N. Greatest integer of 1 by GCD of n comma k.
1 by, no, again.
Greatest integer of
Okay.
1 by
1 by
GCD of n comma k.
n comma, right?
Then we get this sum.
So phi of n is this. At first, can I explain why this is true?
Because it is the number of integers which is less than n or co-prime to n. For co-prime, we get GCD of n comma k equal to 1.
Right.
So this integer will give the value 1, that is integer value 1. Otherwise, it will give 0. So we count the sum.
Indeed,
That is
yeah.
phi n.
So unless if the GCD of this and this is equal to 1, we are getting 0. Yeah, otherwise we are getting 1. Perfect. Yes. And then
Then we break the sum, summation k equal to 1 to n. And we know that summation of d divides n mu d equal to this function.
well, this is just the identity function, right?
Yes.
So this is, okay, let's write it down here. We are from 1 to n, I of GCD of n comma k. Right? Then you want to write I as mu star u, right?
Yes.
Mu star u of GCD of n comma k. Right? And then
Then it is summation.
u we don't need to consider, we just have to take mu because this is ideal one. Alright, so this is summation k running from 1 to n mu of GCD n comma k. Wait a minute. There are some. Very sorry. Yes. There is a summation here. Summation d divides GCD of. Okay, let's just write n comma k. A shortened version for this is okay. So this is right.
Now d divides GCD of n comma k means d divides n and d divides k.
Perfect. Yes. So this is summation k running from 1 to n. Summation d divides n. D divides k. Of k. Right.
Now the sum runs over k equal to 1 to n and d divides k. So we write k equal to some d into some e.
Right. Okay. So we write k equal to d times some e. Okay. Yes.
Now if we fix the divisor d divides n,
Yes.
so the sum will be summation d divides n and the
Summation. Okay. So you want to switch the sums.
yes.
Okay. Yes. So we had k equal to d times e. So e is k by d. So we'll switch. This one here. From here, that is phi n is equal to summation over d dividing n and What remains inside? So this goes out, t divides n, k goes in, and then k is this d times some number e, which is, well, which is, wait a minute, e is k by d, right? And how big can e grow? It can grow up to n by d. Right. So t divides n and e less than equal to n by d. Right. And what do you have inside is
mu of
e of t, which is constant for all of this. So we can take it first. Function d divided n mu d 1 is less than equal to n by d. Right. And then they are basically n by d things. So you have here summation d divided n mu d times n by d, and then you can take the n out. Okay? So you have n times summation d divided n mu d by d. Then
Now we can break this sum as a product of the primes because this function is multiplicative and
yeah, both mu and d, they are multiplicative functions. Right?
so there this sum over the divisors
This is completely multiplicative, but since it is mu d divided by d, it's multiplicative. Right?
So this function also multiplicative total
Yes.
function.
Right.
So we want to check only on the prime powers.
Sure.
And for higher prime powers, this function is 0.
Yes.
So this becomes a product of e, 1 plus mu p by p, and mu
Right.
p is minus 1.
Minus 1. Perfect. Yes. So this, so spreading, so since this is a multiplicative function, what we are using here is that summatory function of multiplicative functions is multiplicative, and that's an easy exercise to check. So here we are using the fact. We also used it earlier when we wrote this, sum over mu d as the sum over the product over the sum of the prime powers. So here we are still using that summatory functions of multiplicative functions is multiplicative. And that is giving you here n times the product over, since it's a multiplicative function, the sum, so we can just take the product of the primes in 1 plus mu p by p, because the higher powers vanish, and then mu p is just minus 1, so we get 1 minus p. Perfect. Thank you. So this is all for today. We will meet again at 11 a.m. tomorrow.